I'm very, very proud to be here to discuss our research at A&M, the research of my team, with my talk is entitled Materials That Move, Structures That Morph, and Their Use in Space Exploration. An outline of my talk, I'd like to give somewhat of a personal and professional introduction, both of myself, my team, my university. Then I'll talk a little bit about the work that we're doing using origami for space exploration, in particular origami that can adapt its shape to change its function. I'll also talk some about the work of my research team on morphic radiators that use shape memory alloys, which are materials that respond to changes in temperature to change how a spacecraft can adapt to environments in different missions, such as. And then finally, because today and yesterday is such a big day for Poland, I'll talk a little bit about our work on spacesuits with 3 former astronauts of NASA in the United States, and how, in particular, spacesuits really need to be different sizes. They need to fit different people, from very large men to maybe very petite women, everyone in between. And so our work in modeling those systems, including thermal aspects and mechanical aspects. So to begin, I did want to, because, Toruniu is the home of the astronomy to much of the world, I did want to speak a little bit about aerospace engineering versus astronomy and how they're related. So to me, the study of astronomy is the exploration of the universe. It's learning the tools, the science, the physics to explore the universe, to get data from the planets, from the stars. And the reason we do that is so that we can understand the universe. So we do astronomy so that we can understand, right, the natural philosophy of what is happening in the universe. Now, as engineers, we use that understanding to change the universe. So astronomy is to explore, philosophy is to understand, engineering is to change. So we take the understanding, we change. The beautiful thing is that once we can develop new tools, we give those tools back to the astronomers. So the engineers help develop the tools for astronomers who study the universe, who help the engineers understand, and it's a beautiful circle of knowledge. And what's also, I think, very interesting, if I pick Dr. Marson from the astronomy department at Nicholas Copernicus University, PhD, and then I am Darren Hartl, PhD, we both have the degree philosophy, doctorate of philosophy. So even though one is an astronomer and one is an engineer, we're both, in a sense, philosophers. We're both trying to understand the universe. And so I think it's neat how astronomy and engineering fit together. Aerospace engineering in particular is the study of making things fly, right? Whether it's through the air or in space. And so aerospace engineers, we study aerodynamics and propulsion. So the flow around the body, like a rocket, the flow out of the engine. We study the materials and structures that an aerospace vehicle is made from. They need to be light and strong. And then we study how to control a vehicle as it's flying. So those 3 things together comprise aerospace engineering. We also study systems design and how humans fit in the system, which I'll talk about today. My particular expertise, though, is, as Magda said, is materials and structures. That is what I focus on. That is what my PhD is from study. I did want to mention that I'm very happy to be in Poland. It's my first time. And it's really only my second time in Eastern Europe, but my entire family tree, all my lineage was from the Czech Republic, from Moravia, from an immigration in around 1900. All of my great-grandparents immigrated from Moravia to the United States and became farmers until about 1950, 1960, and then began to work in factories. And then eventually get to my parents, who worked very hard so that I could be the very first generation to go to the university after the immigration from Moravia. So I'm very excited to be back in Eastern Europe. The last thing about me personally is I have known that I wanted to do this job since I was very young. I'm looking around this beautiful space and I see children playing and learning all around. I was one of those kids one day. And I knew very early that I wanted to invent things, and I knew that I wanted to work on flight. Especially airplanes was my passion. And so when I heard that there was a thing called aerospace engineering, I couldn't believe it. Because I knew I wanted to be an inventor, and I knew I love things that fly, like many of the kids around here. And I didn't know there was a job that you could invent things that fly. And so from the third grade, from third year of school, I said I want to be an aerospace engineer, and I finally did it. So I was very proud. And so here I show some little inventions when I was 7 of, I knew that I can invent a flying broomstick, just like the witch and the Wizard of Oz or Wicked. It was very, very sure that I could do this. So I had very particular drawings, also drawings that showed how you could make a detector that would detect fire. It would use an alarm. And actually, strangely enough, this is the material that I ended up working on almost 20 years later after I do this picture. So it's something that I've always wanted to view, and I'm still very inspired by the children that I see all around this rate. Finally, recently we looked at my own PhD family tree. So the slide shows at the bottom right myself and my PhD advisor. He was originally from Greece. But if you trace our PhD history back, you get into Germany for many, many years of studying solid mechanics, the physics of solids. If you follow that all the way back, we trace our lineage all the way back to Copernicus. So I had to say in Toruniu that my PhD line goes all the way back to Nicholas Copernicus, which many, many PhDs do, but I'm very proud to be one of his tree. Okay, so just a quick on A&M and my lab and what we do. So A&M is a university. It's very large and very traditional. We were lucky to host this past spring some high school students from a high school here in Toruniu, and they were able to visit and see that A&M. I think the culture of A&M matches the culture of Poland very well. A nice tradition, a faith to your family, to where you come from. It's a very large school. So here there's a picture of watching an American football game. 103,000 people fit in our football stadium. So a very huge stadium. But we also have very, very nice scientific research. We have, I think, 4 hypersonic wind tunnels. So wind tunnels that test at Mach 5 plus. We have 3 or 4 of them, and many, many other facilities. Because I'm in Poland, I also had to mention, because I'm very proud, we believe that we have the nicest church of any university in the country. And it's only for the students. It's almost a cathedral, and it's only for the students. It's not for the families or anything else. And that's because we have 70,000 students at Texas A&M. The College of Engineering, just engineering, is 25,000, which is the size of the whole of Copernicus University. Aerospace engineering, we're almost 1,000, so 945. And just to note, the physics and astronomy department at A&M is 350 people. So to give a sense of scale, it's a very big school with a lot of research funding. We can do all kinds of research, and I'll talk about some of that. My own lab, we have currently 12 PhD students, mostly from the United States, a few from abroad, and we're always welcoming students from abroad. Of course, aerospace engineering can be very specific about nationality. There's some countries that we cannot work with, as you can imagine, because aerospace engineering has a lot of defense and space things that we need to be careful. But my lab, as I mentioned earlier, works on the materials and structures of space, as Magda very clearly summarized for you. That's what we do. And in particular, we work on structures that are going to move themselves. They're going to change their shape. They're going to adjust to changing conditions. It's a beautiful area because it combines geometry, material science, and then physics across thermal physics, mechanical physics, and electromagnetism all together. So my students have to be very good in each of these areas. Adaptive morphing structures. Why do we look at them? Well, here's a video of a owl flying at the Royal Veterinary College north of London. And we see as this owl is flying and is coming into land that his wings are changing shape. They're adjusting to flying versus landing. And this is kind of the promise of morphing structure, that I change the shape of my wing or my rocket or my missile or my space radiator as the conditions change. The difficult part about this is that materials for aerospace must be light. Okay, so I can talk about changing shape and how cool it is and very difficult, but if it's not light, it can't fly. And so it has to be light. It also has to carry loads. It has to be strong. because lift on a wing causes, very, very high stresses. I was discussing this with my mother yesterday. Wings have to take very, very high loads. And so I need to be light, I need to be strong, but then I also want to make change shape. And that's a very difficult triangle to do. If it's strong, how can it change shape? If it's strong and change shape, how do I also make it light? And so this is the paradox of my group and what we do in adaptive structures in aerospace. So a famous video that we show is many years ago. For many of the students, probably never seen this, but the older people will know of Terminator 2 and the movie with the liquid metal, and the robot can change his shape and flow, and he can become a weapon. He can move through a prison. So this video, you see the metal becoming the shape of a man. That's the dream, okay? Maybe one day we'll be there. We're not there yet. But what we can do is we can make structures that completely adjust their shape. So you see here an example that uses shape memory polymers or shape memory plastic that's changing the shape of this hand, and that's in our lab. We can use shape memory alloys, which are metals that remember their shape, kind of like the Terminator robot, but not nearly as well. And you see that this robot is moving and crawling as we basically apply heat to different portions of the material. And so with special plastics and special metals, we can change the shape of an object. And that's what we're going to use. In particular, the shape memory alloy is my expertise. And so you see a video here of we apply electric current to a spring. Now, it's not the electricity that moves the spring. If you put electricity on any metal before, your mother told you not to do this, but you put a battery to a paper clip and it gets hot, that heat changes the atoms in the SMA and they make it remember its shape. And so here you see a little spring is picking up a 1 kilo weight, a very heavy weight in a very small spring, just by changing its temperature. And it does that. We use the Texas A&M band to illustrate what's happening. The atoms in the middle of the spring are changing from one shape to another shape in an organized way. The Japanese call this the military walk transformation. So the soldiers shift their shape, the atoms shift their shape, the structure changes its shape, but when you change the temperature back, all the atoms go back to their original position. So you get very large motion that's driven by temperature in a way that's completely recoverable. You can do this 100,000 times and the material will keep working and keep changing its shape. And so now let's apply this to space. So what are the main three challenges of space exploration that we think that morphing materials, adaptive materials can address? One, it's very, very difficult and expensive to deliver things to space. So things need to be light and they also need to be small, right? You have to be light enough to lift and small enough to fit in a rocket, but maybe your system like a solar cell or a large solar array has to be huge to do its job in space. So there's this issue of compactness and lightness that we try to solve. We also need to do many, many functions very far away where there's no one there to operate them. So maybe we forget sometimes that we flew a helicopter on Mars, but we couldn't communicate with that helicopter except with an 8-minute delay. So the helicopter had to be completely autonomous while it was flying. And so we believe that there's some things that shape adapting the structure will help it do many jobs far, far away. So remote operation across many functions. And the last thing is space is an extreme environment. The temperature changes are gigantic, okay? Hundreds of degrees Celsius in a given day or even in a couple hours, depending on how an object is facing the sun, not facing the sun, moving into shadow. You have radiation, and then you also can have very high loads during launch. So it's a very difficult engineering design problem. So my group studies morphing structures and adaptive materials from the ground to space. And from very early ideas, this plot on the left says technical maturity. TRL1 is NASA's way of saying, we have an idea and the computer says maybe it works. TRL6 says we can do an experiment and we're ready to do a flight test. TRL7 is a flight test up to TRL9 is right now, Miroslav is flying TRL9. He's actually doing it. My group works TRL1 to 5 as shown in this plot. So from an idea, computational, all the way to very good prototypes being tested at NASA. So I will talk about 3 examples. The first one is origami for space. So here, most of you that have an interest in watching this video probably know what this is. the most amazing astronomical instrument and maybe in existence right now, the Webb telescope. And if you look at how the Webb telescope is made, it's got patterns, facets that are folded together, right? Because this very large lens had to be stored in a rocket. And because we were able to fold this thing up, we're able to get these beautiful images like I show here. There's a famous origamist named Robert Lane from the US who is an artist. He folds very, very complicated structures, but he's also been working with NASA and JPL to create even more complex folding lenses, to create even bigger telescopes that could be, again, deployed. And so origami allows us to fold up into a very compact shape, but it also gives us a way to change the shape, because if I can move the folds, I can adjust the shape of a lens or a structure. By the way, I mean, a great example that we're all using, you don't know, is the airbag in your car. Is a large bag compacted into a very small space in your steering wheel. They use origami to figure out how to fold the bag into such a small space. So I say here, origami enables astronomy, because if we can fold up these devices, which would create these very, very amazing systems. So what my group did is, this is one of only 2 math equations you're going to see. You don't need to memorize, there's no exam. But just the idea that we need some very, very complicated mathematics to describe how to fold the structure. And in particular, how to fold the structure when the structure has thickness and it has some roundness in the folds. And so we even have a book that we published on, it's called Active Origami. It's how do we fold up structures. And if you see this video at the bottom, as I'm talking, this antenna is folding itself up. This isn't a furnace. This is using the shape memory polymer to fold a flat sheet up into an antenna. And over time, it folds up. Here's a very complicated example of what's famously known as the Stanford bunny. It's a shape that's very difficult to model. And so this system of math and computation developed exactly the fold pattern to take a flat sheet into a bunny. If we can fold a bunny, we can fold an antenna. And so, and then I go back and I show the observatory that we have in Texas, and you see this meshed, complicated shape, right? Origami allows us to get from flat or rolled up to very, very complex shapes. And so what we studied was using, perhaps say we wanted an antenna that is facing the ground. And we either want to send a signal or receive a signal from a very particular shape. And we kind of made up this problem to look at, could I combine origamis and antennas and reflectors? And so I have an antenna, I want to point it at a country, and I only want to send or receive to that country. Could we fold an antenna to do that, and could we change its shape? So we use origami to take this smooth dish and make it into many facets. We came up with a fold pattern so it could fold itself up. But then we added the shape memory alloys to each fold so that we could move each fold and change the shape of each fold. And then that would allow us to change the shape of the whole antenna. So each of the slices of this antenna has 3 SMA wires on the back. And so we're able to start to do some analysis, and we see, okay, if we actuate different wires, different amounts, the antenna begins to move, or piece of the antenna begins to move. We understand that. The students spend 6 months understanding how to do the shape of alloy, how to adjust the antenna. If I heat, this plot here shows if I heat different regions colored in blue, I get different shapes. Then we combine all that together and we say, okay, what if we only want to send a signal or receive a signal from the United States? It has a strange shape. Florida is down there, it's long. And so we look at which wires should we actuate, and can we design the antenna to kind of focus the signal? And so if we don't actuate any, we get kind of big, broad signal. And it shows some examples. If we actuate just one slice, it shifts the signal. If we actuate the slices on the side, it begins to narrow the signal. Then we do a large optimization problem. So this compact, very complicated plot is showing that we ran 500 analyses, because if we can do this complicated design in a computer, I can try many, many, many designs much faster than we can do by building a prototype. So this would be very important later when I talk about the spacesuit. It takes maybe $1 million to build a prototype of a spacesuit where I can test many designs in the computer, thousands of designs, much more quickly and much more cheaply. Here we're applying it to the antenna, and we study and study and study and try and try and try. And there's a focused way that the computer is learning which actuations give you the right shape. And at the end, we find a shape that tries to keep here, it's colored in green, the green signal inside the United States. We try to have the least blue, which is signal outside of the United States, and the least red, which is regions of the United States that are getting no signal. So I want lots of green, no blue, no red, and this antenna configuration that actuates these SMA wires gives me a signal that focuses on the United States the best. So that was an example where we said, okay, I have origami, I have active materials, I have space, let's combine them and see if we can solve a problem. That was some years ago. Now, even today, we're working on morphing space radiators for NASA. And so this is a different problem. Here, we're trying to change the amount of heat transfer out of a spacecraft as the thermal conditions of the spacecraft change. So I'm going around the Earth and I'm seeing the sun, then I'm in the shadow, or maybe I do that a couple times and then I head to the moon. And so on the way to the moon, it gets very, very cold. I have dark space all around me. Then I get to the moon, and now the moon is reflecting the sun's energy back at me. All the time, the thermal conditions are changing. So it's like you sitting here today, I turn on the air conditioner, I blast on you, then I turn it off, then I bring a heater, then I tell you to get up and run on a treadmill. You'll be getting hot, you'll be getting cold. And so we want to make a system that can help the astronauts and the space systems adjust to all of those changes. So probably I'm the only person to give a talk in this venue to show pictures of puppies. And so I love this slide. When puppies get cold, they curl up into a little ball, like this cute puppy here. When the puppy's hot, he spreads out, right, to cool off. What if we could use active materials to change the shape of a radiator to do the same thing? To open up to space when I need to get rid of heat and to close and protect the heat when I'm very cold. And so because spacecraft do the same thing, they get cold, they get warm. And we need to change the way that we get rid of heat. The only way to get rid of heat in space is radiation. There is no air to blow on you. There's nothing to touch to give my heat away. The only way to give heat is to point a hot object to space and use the physics of radiation to get rid of the heat. So the space shuttle had radiators. The space station, where Miroslav is today, has big radiators to get rid of the heat. So the problem, as I mentioned, is that the conditions are changing all the time. And assuming again, we want to go to the moon. When I'm on my way to the moon, the astronauts are resting, perhaps. The computers are turned off, the systems are shut down, and space is very, very cold. So I have very low heat rejection need, only maybe 500 watts, a couple of light bulbs, large light bulbs. But the outside is very, very cold. So I'm not producing any heat and I'm surrounded by very cold space. Then I get to the moon and I'm getting ready to land, and now all the systems are up and I have 4,000 watts, all right? Like 4 or 5 microwaves turned on, and the temperature is now very warm. So how do I make a system that can change how much heat it gets rid of? That's what's challenging. And right now, the best system can change that amount of heat 3 to 1, 3 times to 1. We need 10 to 1. Okay, so we want to develop a system that can change the heat rejection 10 to 1. And NASA says, you can see some NASA language here, that the most critical thermal technology is radiators, and we need to be able to vary the heat rejection. And NASA says one of the best ways to do this is shade memory alloys. Lucky me, my group does that, so we do a lot of work in this area. So the second slide that has math is very simple. If you've had high school physics, or depending on your education, if you've ever seen how radiation gets rid of heat, it's really simple. There's a constant called the Boltzmann's constant, here represented by sigma. Then there's the emissivity, which is how shiny or flat a surface is. Okay. Then there's the area of the surface. And then there's the difference in temperature between me and the environment to the 4th power. So it's just multiplication. Boltzmann constant, emissivity, area, difference in temperature. And again, maybe you learned that in high school physics or early in college. But light is a little more complicated than this. This is the simple way we learn. There's one more term, which is called the view factor. So in real light, if I have a surface and I want to reject heat to another surface, so my hand here and my hand here, and I want to move heat, there's also how much, they call view factor, how much of this surface can see this other surface. Now that's very important in space, because if I want to reject heat to space, I need a very high view factor to space, and I can't be hidden by other things, right? So there's my area, there's how shiny my surface is, there's how hot I am, and then there's how well can I see space. And we can, because I can change that, I can change how well I see space by changing the shape. Now my research team has something to do. If I can change the shape, I can change how well I can look at space. And so that's the physics that we're going to use to design these systems. So very early on in 2014, 15, we started to design a radiator that could open itself up, like the puppy in the picture, or you can think like a flower opening itself to the sun. So these radiators using shape memory alloys, as the radiator gets more warm, or as the environment gets more warm, the SMA is getting warm, the atoms are going through this military walk transformation, and they're bending the radiator open, like you see in this computer picture. And so it was showing at the bottom that we have computer codes that look at how hot the SMA is, and then they take the temperature and they send it to a mechanical analysis, and it says, okay, well, if you move this much, you should open up this much. Then it takes that to the thermal analysis and it says, well, if you're open this much, you should reject this much heat, so you should be this temperature. It takes the temperature back to the SMA. And so the computer codes are talking. And this is the beauty of aerospace engineering and engineering and physics in general, is again, we have to consider multiple physics at a time. The thermal physics, the mechanical physics, the equations of radiation, all are being encompassed in a computer. And that's great because I can design the radiator by trying many, many different designs in the computer. And so I had a couple of students who created this code. Then, of course, I need to go build them. Okay, if I make one in a computer and I tell NASA, look, I have a solution for you, they're going to tell you, go back to Texas A&M and go work in your lab. We don't believe you. You have to make prototypes if you want the world to believe your work. And so then we took this design, and you can see in this video here, this is at NASA Johnson in Houston, famous Houston, the evil has landed. Houston, we have a problem. Right there, where they said those words, we're testing this radiator. You see 5 of them together opening up. And as they open up, they're rejecting heat. And so we were able to show that the morphing radiator did exactly what we thought, that it can change its shape and change the amount of heat rejection. I like this picture with Priscilla and Colette, because we did a lot of this work during COVID. And you can see they have the face masks on. And we were trying to finish this research right when the world was saying you need to be separated. And so it was very difficult to try to find some conditions where we could build these prototypes. But we did it. And in fact, over time, we've done many of these. We started with very simple prototypes on the left. You see my son is very young there, all the way to 2024, where we're working on some new concepts. And I had to tease my son that, he was little in this picture, and now this summer he was working on a big Texas ranch. He thinks he's a tough guy. He sent me this picture a couple of days ago. So there's, how time goes by. I thought it was neat to show. So then we can take those same ideas and actually start to apply them. What if we're actually going to operationalize this? So instead of just an idea and it works, okay, now let's come up with a mission. And that's, as you get to the high TRL levels of NASA, technology readiness level, you actually have to start thinking of the mission you're going to accomplish. So we started looking at data from the moon. How hot does the moon actually get at a certain latitude where we're thinking about doing some lunar missions? And so we have real data on temperature. And so we start to tune the radiator to work at that location on the moon. And so we're back to the computational design. This is the most recent model that we have. It has fluid flow. You can't see it, but the fluid is flowing, changing the temperature, all for a very particular location on the moon. But then we thought about this problem some more, and we said, it's very challenging to bend something open and close. I mean, we can do it. We proved that we could do it. But maybe it's better if I want to change the area of a radiator, maybe instead of bending, because bending a structure, I risk breaking it, right? If I bend it, I may break it. What if we could just rotate and use an SMA tube that's twisting to take flat, strong panels and rotate them? Like opening a book. Okay, so I have 2 flat sides and I open like a book. What if we could do that? And so We went back to the equation and we said, basically we could derive the math for how the view factor will change as I open the radiators. And we did some computer analysis. We said, yes, this will work really well. So then we started building with, again, you must build a prototype in engineering. And so we started to build an early prototype. Again, the SMA2 here, circled in red, is as it gets hotter, it's twisting itself. Okay, this video has no motors, no sensors. It's just a metal at the hinge, like the hinge of your door. The hinge itself is a living hinge. The metal is twisting itself and twisting the radiator panels. We believe this is a much better engineered solution. And so now we're looking at other lunar operations where we're working with the power group at NASA to look at fuel cells that need to change the amount of heat they reject during the day on the surface of the moon. And so this is only 3 months ago, developed the first prototype for that system. And so it looks similar to the other video where the panel is rotating, but it's actually a much more complicated system that has no pumps, and it's using a heat pipe to move heat. Many of your laptops are using a heat pipe, but your laptop is not morphing itself. So we use the same kind of thermal management from your laptop, but also adding a living metal. So now we're moving heat and moving the radiator in a combined area. So my last topic I'll talk about, this is not adaptive structures, it's not morphing materials, but it's going to use the same physics to look at spacesuit design. Again, remembering the auspicious days that we're having here in Poland. And so, excuse me, at A&M, we're very lucky to have 3 astronauts in aerospace engineering as teachers. Dr. Tramatov had 5 shuttle flights, Dr. Dunbar had 5 shuttle flights, and Dr. Nancy Curry-Gregg had 4 shuttle flights. And so they have a lot of experience with NASA, and they're all interested in how we can do better in human spaceflight. So what are the engineering challenges to design a spacesuit like you see here behind me? It needs to do about 8 things all at the same time. It needs to give to the astronaut enough pressure. Space is a vacuum. Human bodies need pressure to survive. So that it must give us pressure. It must give us oxygen. It must take away carbon dioxide. I need water. That's kind of simple. I can do a camelback kind of thing. I need power. I need communication. I need temperature control. So I need to stay cool, kind of like the radiators earlier. And I need to protect myself from micrometeorites and radiation if I'm in space. All of that, and I still need to be able to move my fingers. Okay, I still need to be able to bend my arms. So I can't be in a rigid thing flying around doing all the other 8. I need to be able to move. That's incredibly challenging. And so if we look just on this spacesuit, just at the elbow, just starting at the elbow, it needs to accomplish, it needs to address pressure, temperature control. So it needs to have some insulation to keep my arm warm. It needs to be strong against micrometeorites. So it needs many layers, including Kevlar. And then it needs to move, right? If I can't bend my arm, I'm not an astronaut. So that's what we're working on. Okay, so that's challenging enough. That's all very, very hard. Now let's add another challenge. Dr. Dunbar and Dr. Nancy Curry-Gregg were early women that flew in space. These women had very different body shapes than the men that came before them. Bonnie Dunbar, for example, when she flew in the US, they would take pieces of men's spacesuits and give them to her, and she had to try to move. And it was very uncomfortable. And only when she flew with the Russians, actually, did they help her fit her suit to her body. And so she made it a focus kind of her life to be able to make spacesuits that fit each body, okay, so that everyone can have access to space. Nancy Curry-Gregg holds the Guinness Book of World Records for the shortest person in space. She's 152 centimeters tall, 5 feet. She's the shortest person ever to fly, and she flew 4 times on the space shuttle. She said no spacesuits fit her because they're sticking her in men's suits and nothing is the right size. And she said her elbow was not matching where the suit was bending. And so again, we want to create a way to engineer very complicated spacesuits for all kinds of people. Very large men to very small women. If we, thinking of Miroslav here in his spacesuit, there are 41 different body measurements that are used to kind of try to tailor a spacesuit to a human being. And so body shapes are very complicated and the proportions are different. You can't just say, well, I'm 170 centimeters tall, so my arm is so many centimeters. No, people have long arms, long legs, short legs. All these measurements that you see in the slide are kind of independent of each other, and they all go into how do we design the spacesuit just for you. It's also complicated. I mentioned all the other complexities. In terms of thermal design, underneath all of the spacesuit is what's called the liquid cooled and ventilation garment. So you can't really see, but this suit has little tubes, like straws, all throughout that are taking the heat away from the astronaut, or warming the astronaut if the need be, as the situations change. So I need to design a system that has a fluid tube suit that can fit any body size or can change. That is what we're working on doing. And so just in the last, even today, my student is working on taking those measurements and creating a thermal model where we can completely understand the heat distribution in the body. Right now with this hot light and I'm wearing this coat, I'm starting to get pretty warm. And so it would be awesome if I had a fan, which I don't. And so you can imagine the astronaut's going through the same thing. Maybe he's out or she is out there working very hard, working on the space station, starting to get sweaty. Their core temperature is going up. And so we're able to design, we have a model that's completely scripted, means it automatically takes body measurements and forms the model to those measurements, including how the flesh is distributed inside the body. So shown here, a thigh has a certain distribution, the bone, then muscle, then fat, then skin. The shin has different bones in different places, much less fat. All of that we consider throughout the body. And what it lets us do is do full analysis of all the temperature throughout the body in different conditions. So this is showing resting temperature in Kelvin for a very small woman versus first percentile woman, the smallest woman of the population, to a 99th percentile male, a very big man. And so all in between, we can look at as they're resting, what is their temperature distribution? If we allow them to exercise and then add some cooling in the garment, what the temperature will be through the body. Now, these results are preliminary. I'm not saying that they're perfectly accurate. The student is working, her name's Maddie, and she's at NASA today, still working on this model. And so some of these are the early numbers that we're getting out, but they match the right amount of temperature in the body to be healthy. So now we can start to design the spacesuit. And the last technical slide I have that's the thermal. Now we talk about the mechanical and the mobility. And so, again, my group can do this because we model changes of shape. We model changes in temperature. So spacesuits, sure. And so here you see a bad example. What if the arm was just a big inflated bag and I needed to try to bend it? And you can see in this picture exactly what would happen. It's very, very stiff. Then you get a big wrinkle and it collapses. You see that an arm couldn't fit in here. What we need to do is add multiple layers. So you have a pressure layer, you have the outer layer, then you have these sewn panels that are sewn on, and that gives me mobility. Now the arm bends easily. It has room for the arm to fit all the way around. And what that allows us to do is we can do a design study for your body that tell me where to put the elbow fabric relative to your actual, bone joints, how many of these fabric, we call them gores, that you should sew, and how thick the layers should be. All of these aspects we can design in the computer so that we can build the perfect suit for your body. That's the idea. So to summarize, engineering for space is very difficult. We identified a few challenges, extreme environments, remote operation, difficulty in delivery. Adaptive structures and materials that move allow us to unfold and deploy large structures. And they allow us to move the structures and change them to adapting conditions, like the radiator. And if we do the thermal and mechanical design of spacesuits in a computer, then I can design a spacesuit just for your body, as unique as you are. And so that when you go to space, or your children or your grandchildren go to space, hopefully then we can have a suit that's perfectly matched for you. Professor always must show where his funding comes from. So you see here, the emblems that you see the most are NASA. I get much of my funding from NASA in the United States and also the United States Air Force because I study aerospace. The Air Force and the Department of Defense also have high interest in space and, of course, flight. And so I'll end with a quote that when I think about mentoring my students, Sir Richard Branson said that you should, when you have people working for you, then you should train them well enough so they can leave and go have better jobs, but you should treat them well enough so that they never want to. And so I believe very much this is how I treat my research team is I train them to have every skill to go out and change the world of space exploration. But as you can see in these slides, we also have a lot of fun. So maybe they never want to leave. I don't know. So with that, thank you.